Good evening. We are now going into the second session of the fourth chapter, Magnetism and Moving Charges. The first session we dealt with Biot-Savart law and its application. One application we have, that is we used Biot-Savart law to find out the magnetic field along the axis of a circular loop carrying current. Now our next session is Ampere's Circuital law. So if you remember, I told you that Coulomb's law and Biot-Savart law are similar in that they are inverse proportion. That is, they are inversely proportional to R square, both of them. Now this Ampere's Circuital law, we have this. Next thing that we are going to learn is Ampere's Circuital law. Is very similar to your Gauss's law in electrostatics. So we use that Gauss's law, if you remember, to find out the electric field due to, first we did, there's a straight conductor carrying charge, a straight wire carrying charge, and we used the Gauss's law to find out the electric field at some distance r. Then we used Gauss's law, we had a plane sheet which is charged. We used Gauss's law to find out the electric field at a distance r from the plane sheet, charge sheet. Then the third application was we used Gauss's law to find out the electric field due to a hollow spherical shell which is charged. In the same manner, in this chapter, we are going to use this Ampere's Circuital law to find out the magnetic field due to a straight conductor. You already know that a straight conductor has a magnetic field given by the right hand thumb rule. This you learned in 10th standard, where if the thumb gives you the direction of current, the curling of the fingers gives you the direction of magnetic field. So that means your magnetic field will be in circular loops around your conductor like this. So to find out the magnetic field at any point P, which is at a distance r, you can use Ampere's Circuital law. Then you have learned about the solenoid. Solenoid, when you learn the electromagnets, solenoid, then we have something called as the toroid. So all these things we can use Ampere's Circuital law to find out the magnetic field. So that's what we're going to do now. First, let us state Ampere's Circuital law. Ampere's Circuital law states that the closed line integral of B dot dl, both vectors, must be equal to mu 0 times current. Now let me first explain this to you and then we'll go on to the applications. Okay. Now here, I'm going to introduce something called as the Amperian loop. It's called the Amperian loop. Just like we had Gaussian surface in the first chapter, we have the Amperian loop in this chapter. What is Gaussian surface? Gaussian surface is any closed surface that encloses a charge. If you remember, for our first derivation, we enclose this line, this charged wire inside a imaginary Gaussian cylinder. And the second one, the plane sheet, we enclosed within a imaginary Gaussian cylinder. And then last one, in that spherical shell, we enclosed within a spherical Gaussian sphere. In the same manner, so you would have noticed that a Gaussian sphere is any closed surface that encloses a charge, and the charge is the source of that electric field. The electric field is because of that charge. So please understand, Gaussian surfaces are closed surfaces which encloses a charge where the charge is the source of the electric field. In the same manner, let's say we have a conductor like this which is carrying current. And because of this current, at a point P we have a magnetic field. So this magnetic field, the source of the magnetic field is a current carrying conductor. If you enclose this source, that is the current, inside a closed loop, then that loop is what you call as the Amperian loop. So that means if your source of the magnetic field is a straight conductor carrying current, and I enclose this straight conductor carrying current, which is the source of the magnetic field, with a loop, then that closed loop which encloses the current is what you call as an Amperian loop. Now this Amperian loop, I'm going to divide into small sections of length dl. So here I have a small section of length dl. Okay. So this whole Amperian loop I can divide into small sections of length dl, where dl, the direction will be along the tangent. Simply because your Amperian loop is circular. So at any point, if you take the direction of the vector, it has to be along the tangent. Please understand that this dl and the one that I introduced in Ampere's circuital law are different because here this dl is a current element I told you. dl is a small element which carries current and it has a direction in the direction of current. But here this dl is not a section of this current carrying conductor. dl is a small section of that Amperian loop and that at a point will be directed along the tangent. Now for this conductor, the magnetic field also happens to be a circular loop, right? By right hand thumb rule we know the magnetic field also happens to be a circular loop. So that means at the point P, this magnetic field is also a circular loop and therefore at this point you will have the magnetic field also along the tangent. So everywhere along the loop, the Amperian loop, the section of the Amperian loop dl and the magnetic field both are circular for a straight conductor. So both will be along the tangent. So I hope you have understood clearly what dl is in this portion. Here dl is a small segment, infinitely small segment which is part of that Amperian loop, and an Amperian loop is a closed loop which encloses the current where current is the source of that magnetic field. Then magnetic field, the dot product of these two vectors B dot dl when integrated over the closed loop. This sign here tells you that you are going to integrate it starting from here and ending here along the closed loop should be equal to mu 0, which is the permeability of medium, mu 0 times the current in that enclosed by that Amperian loop. So mu 0 times I, please understand, will be the current enclosed by the Amperian loop. So I hope this Ampere circuit law is clear to you. Closed line integral, you integrate over the whole closed loop. The dot product of B dot dl will be equal to mu 0 times the current that is enclosed by the Amperian loop. Okay. Now we can apply this Ampere circuital law to find out magnetic field due to this conductor. So the first application in your textbook is to find out the magnetic field due to a straight conductor, which is infinitely long straight conductor which is carrying current. So infinitely long straight conductor that is carrying current. So we have magnetic field due to an infinitely long straight conductor which is carrying current. Okay. So I am drawing this current carrying conductor, straight conductor here which carries current I. Then I need to enclose it. If I need to apply Ampere circuit law, I have to enclose it inside an Amperian loop. So this is the Amperian loop that I am drawing, which passes through that point P where I am going to find out the magnetic field. So this point P is at a distance R and we are going to find out the magnetic field at that point P. Okay. Circular loop. Now because I am going to apply Ampere's circuital law, I am going to take a small portion of that Amperian loop which I call dl, and dl should be along the tangent because the Amperian loop is circular and dl is a small portion of the Amperian loop. We know for this current carrying conductor, we know that the magnetic field is also a circular loop. So at point P, the magnetic field also happens to be a circular loop, and therefore magnetic field and dl both are along the tangent at every point. Okay, now closed line integral B dot dl, if I am going to integrate, I can take B outside and integrate only dl. So this happens to be B into, if I integrate and add up this whole thing, this is going to be 2 pi r, the circumference. So that is 2 pi r. That is my first equation. By Ampere's circuital law, we know that this closed line integral B dot dl must be equal to mu 0 I. That's what we know from Ampere's circuital law. So that is equation 2. The left hand sides of both the equations are the same. So I will equate the right hand sides to get B into 2 pi r must be equal to mu 0 I, or from there I know this is mu 0 I by 2 pi r. Okay. So we got the magnetic field at a distance r given by mu 0 is the permeability. I is the value of mu 0. Please remember, I told you mu 0 by 4 pi is 10 raised to minus 7. So here you will substitute mu 0 as 4 pi into 10 raised to minus 7. Okay. Now, I is a current enclosed by the Amperian loop, 2 pi, and r is the distance at which, distance from the conductor where you are asked to find out the magnetic field. Then there are two more applications in the textbook, but in the new syllabus and even last year, that derivation was deleted. You don't need to, you just need to have qualitative idea. That means you need to have only the final formula to do sums and to apply elsewhere. So you don't need the derivation for that. That is, next one is for a solenoid. Even though in the notes that I am sending you, think it is there. Let's see. You don't need the derivation, okay? So we have solenoid looks like this. I'm sure you learned this in 10th standard. You've seen this in 10th standard. And you know that the magnetic field is along the axis. Like this. This is the magnetic field existing along the axis inside the solenoid. And the formula for this is mu 0 n into I. You don't need the derivation. Here n is small n is the total number of turns divided by the length. That means if you have total number of turns as n, capital N, and let's say the length of the solenoid as capital L, then the number of turns in unit length is what you have as small n, that is n, and I is the current that is passed through the solenoid. This will give you the magnetic field along the axis of a solenoid. Now what we have as a toroid, the next one what we have is toroid. Toroid. T-O-R-R-O-I-D. If you take the solenoid and bring it into a circular shape, then you call it as a toroid. A toroid is an endless solenoid because in a solenoid you have the magnetic field like this. So one end will be north and the other end will be south. But if you turn it and then fix it like this into a circular shape, then it doesn't have any north pole or south pole. So it's just an endless magnetic field without a definite north pole or south pole. So this is how it will look. Like this. So your current will enter here and your current is going to come out like this. So what you had as a solenoid like this, where magnetic field like this, you had a north pole and a south pole. You just put it into a circular shape, fix it here. So there is no definite south or north. It's a continuous field like this. And that is what you call as a toroid. This is what you call as a solenoid. For this also, the magnetic field will be along the axis inside here. The magnetic field will be along the axis like this. And that magnetic field is given by the same formula, mu 0 ni, where n again is small n will be the total number of turns divided by the total length. The total length of this axis will be circumference of that circle. So from here till here, if it is small r, you will have 2 pi r as the small n. Okay, because this length in which you have n turns is 2 pi r. So you don't need the derivation, but you need to know the formula. Next, what we are going to look into is the Lorentz force. Lorentz force. The magnetic Lorentz force. This is what we are going to discuss now. Magnetic Lorentz force. Now in electrostatics, we have the force acting on a charged particle as QE. Relatively simple, simply because even though the force is a vector quantity, it will have the same direction as the electric field, because Q being a scalar, electric force will always be in the same direction as electric field. So even though force is a vector, not much confusion, because if you know the direction of electric field, you know the direction of force acting on the charged particle. F equal to QE, electrostatic force. Now the magnetic force acting on a charged particle, that means when a charged particle enters a magnetic field, the force that the magnetic field will exert on it is given by magnetic Lorentz force, which is F equal to QVB sine theta. And I told you, when you see sine theta, you will know that it is a cross product between two vectors. So we may write the vector F is equal to, Q is a scalar, the two vectors are V and B. So V cross B, where theta is the angle between the velocity of the particle and the magnetic field of the particle. Now from this equation you will see this is slightly more complicated than the electric field or the electric force, simply because this force will not be in the direction of V, will not be in the direction of B, because it is a cross product. It will always be in the direction perpendicular to V and B. For example, if this is your plane containing V and B, okay. Now always it will be V to B, QVB sine theta. A cross B is not equal to B cross A, because A cross B and B cross A will always have opposite directions. So you have to take this vector product as V cross B, not B cross V. So if you have something like this, the plane containing the vectors V and B is this plane. So the vector force will always be perpendicular to this plane. That means you could have the force perpendicular like this or inwards. Okay. Now you will see in this case V cross B is in clockwise turn. That means your vector force will be perpendicular to the plane containing V and B, and it will be inwards. So if it's like this, your V cross B is inward force like this. Okay, in this particular case. If you had B here and B here, then V cross B would have been an outward force. Or V cross B would have anti-clockwise turn, means upwards or outwards. Okay, so that's why I said this is slightly more complicated than the electric force that we learned. Now you will see, if your charged particle in the magnetic field is at rest, it's not moving. If V is 0, then force is also 0. It will continue to be at rest as if the magnetic field does not exist, because the moment V is 0, the magnetic field does not exert any force on the particle. Also, you will see that if you have let's say your magnetic field is in this direction, okay, the particle is entering the field with a velocity parallel to B. Then what happens? Angle between V and B, both are parallel, so theta is 0, which means force is also equal to 0, because sine 0 is 0. So no force is exerted by the particle, exerted on the particle by the magnetic field if V and B are parallel. Same case, if B is in this direction and let's say V is anti-parallel, then what happens? Theta is 180. Between V and B, the angle theta is 180. Sine 180 is also 0. In that case also F becomes 0. Now so that means there is an important understanding from this. What is work done for you? Work done, small work done by the magnetic field is F dx cos theta. Okay. In both these cases F is 0. If F is 0, whether cos 0 or cos 180, don't bother. When F is 0, work done is 0. Now you have learned in 11th standard, work done is equal to change in kinetic energy. So as this particle enters parallel or anti-parallel, with its velocity parallel or anti-parallel to the magnetic field, what is happening is there is no force acting on the particle, and therefore there is no work done on the particle, which means there is no change in kinetic energy. So your particle will continue to move in the same direction without any change in its velocity, because no change in kinetic energy. So basically if this entered with let's say 5 meter per second, it will continue with the same direction and same magnitude, no change in velocity. either in magnitude or in direction in both the cases. So what are we saying? It'll behave as if the particle will behave as if the magnetic field does not exist at all, no deflection produced. Okay. So that after that, we are now considering a second case. So we discussed the case where theta could be 0 or theta could be 180. Now in the third case, we are going to see what will happen if theta is 90. Okay. So let's take B perpendicular to B, which means theta is equal to 90 degree, and we also should know that this will be the maximum force because the sine 90 is 1. That's the maximum value of sine theta. So maximum force is acting on the particle. But let's see what happens to the direction of the particle velocity. Now I told you in the previous section, if you see a cross, then you must know that the magnetic field that I am representing is perpendicular to the plane of the board and inwards. If you see dot, then it means that the magnetic field is perpendicular and coming out like this. Okay, it's basically the arrow. If you know how you draw the arrow, right? At the back you have that feather thing, and that is what is represented by the arrow. Here the cross, and in the front they represent it with a dot. So if it's coming out, then you will see the dot. If it's going in, then you will see the cross. So if you see something like this, please understand that the magnetic field is perpendicular to the board and into the board. This is the direction of magnetic field. Now let's imagine a particle is now going to enter like this. Its velocity is perpendicular like this. This is the velocity of the particle. So now maximum force is going to act on it because your particle velocity is in the upward direction, but your magnetic field is into the board like this. So they make an angle of 90. So particle velocity is upwards, the magnetic field is inwards, and so they make an angle 90. So maximum force is acting on it. Now I told you already that if you have, let's say B is like this, right? B here and V here. So now I'm keeping the plane like this, where B is into the board, velocity is upwards. Can you see that? V and B. So this is how it is. Now you see that V cross B is taking a clockwise turn. And if it's taking a clockwise turn, you know that the force should be perpendicular to this plane and inwards. So if I keep it like this, with the velocity of the particle in the upward direction and magnetic field here, the force is going to be, here it is in the clockwise direction. So the particle is going to experience an inward force. So you will see this particle will be pulled in by an inward force which is QVB. So your particle which had started off like this cannot continue like this because it is acted upon by an inward force, and so the particle will now turn and let's say reach here. Reach here. So now at this point I am going to mark its velocity in this direction. Okay. So now what has happened? Your velocity is now in this direction, right? This is the plane I am using. So your velocity is in this direction, but your magnetic field continues to be inwards. It's still inwards. So see this? Your velocity is like this and your magnetic field is like this. The force has to be perpendicular to this plane. And as I turn from V to B, you will see it's again a clockwise turn. It's a clockwise turn. And so your force will be perpendicular to the plane and inwards. So that means here again it is going to experience an inward force. So your particle can't continue like this. It will have to now turn. So now along the tangent the velocity is here. If you apply the same logic, here again the particle will be pulled in with an inward force. So your particle can't continue like this. Instead we'll have to take a turn. Velocity at this portion is V here. Again inward force. And so you will see your particle, when you had a magnetic field in the inward, your magnetic field was like this into the board. Your particle entered like this. Maximum force is acting on it. But what happened? It can't continue. It started off like this. It can't continue in its original path. Instead, it will have to now exhibit or circular motion like this, with the plane of that circle will be perpendicular to the magnetic field. If this is a circle, the plane of that circle will be perpendicular to the magnetic field. Okay. So I hope you understood this, how we have an inward force and how the particle who started off in the upward direction, initial direction we are given this, instead of continuing in this direction, it will now execute circular motion with the plane of the circle perpendicular to the magnetic field, and the force acting on it is QVB. So from this you will see the maximum force QVB is what gives it the circular motion, and the circular motion you already know from 11th standard has the force called as the centripetal force, which is equal to mv square by r, which is the centripetal force. Now if I cancel this and this here, we see that the radius must be equal to mv by qb, where m is the mass of the particle, v is the velocity with which it entered, q is the charge of the particle, and b is the magnetic field. So the radius for a given particle, so here if you have a given particle whose mass and charge are constant, and the magnetic field is also constant, the radius is proportional to its velocity. Okay. Then from this you will see, from last year, remember what we did as angular velocity omega. We have learned v equal to r omega. So from there, omega is equal to v by r. This you have learned last year in motion in a plane. So this is angular velocity v by r. From this equation, v by r you see is v by r is qb by m. Omega is, I hope you know, 2 pi by t or 2 pi nu. So nu, 2 pi nu is qb by m, where nu is the frequency of the particle, or nu is equal to qb by 2 pi m. Here q and m are the charge and mass of the particle, b is the magnetic field, and nu is the frequency. Frequency is the number of revolutions in 1 second. This you know is inversely proportional to time period. So time period will be 2 pi m by qb. What do you mean by time period? Time period is the time taken for this particle to complete one revolution. I remember this portion we have done in motion in a plane. I told you it will be carried over to the 12th standard. So these formulas, if you don't remember, please go back to class 11 textbook, motion in a plane. Now one more thing I need to discuss here is that let's look at the work done in this case. Work done, dW, you know, is F dx cos theta. Work done is F dx cos theta. Okay. Theta is the angle between F and displacement. Displacement is in the same direction as velocity, right? Because velocity is displacement by time. So if this is the velocity direction, this is the same direction of displacement. Force is centripetal force towards the center along the radius. So this is the tangent and this is the radius, and you have an angle 90. Always in circular motion, the displacement or the velocity is perpendicular to the centripetal force, which is always along the radius. So we have theta here as 90. So this is F dx cos 90. Cos 90 is 0. And here again we see there is no work done. So please note, the magnetic field was unable to do any work in the first two cases, theta equal to 0 and theta equal to 180. In this case also, the magnetic field does not do any work even though the maximum force is acting on the particle. What does that imply? The velocity of the particle, suppose it entered with, let's say, it entered with 5 meter per second. The magnitude of the velocity will remain the same, no change, because how can it change? Work done is change in kinetic energy. Work energy theorem states that in class 11. So work done is change in kinetic energy. If work done is 0, change in kinetic energy is also 0. So kinetic energy half mv square, there is no change in the magnitude of v, but still it is an accelerated motion, because at every point circular motion means it is keeping on changing its direction. The direction is along the tangent, and so we call it accelerated. simply because its velocity changes in direction but not in magnitude. So the magnetic field is unable to do work in all these cases. It doesn't do any work. What does it do then? It changes the direction of motion. Your particle, which is supposed to go straight, has now been put into circular motion. And the last discussion on this will be, suppose you have this particle entering the field with some arbitrary angle theta other than 90, other than 0 or 180. Let's say theta is 45 or theta is 30 or theta is 60, any other arbitrary angle other than what we discussed now. Okay. So let's see what will happen in that case. So we have the third case where we have theta is some arbitrary angle. Okay, so we have, let's say this is the magnetic field B, this is the velocity, the two of them make an angle theta other than 0, 180, 90. All those three cases we discussed already. Now this V I can resolve into two components. This is the adjacent component, so this component is going to be V cos theta, and there is another component, the perpendicular component, that is a V sin theta, right? Now you will see here, the component of velocity here, V cos theta and V are parallel to each other, which is the first case that we discussed. So if velocity and B are parallel, then it means that the force is 0, remember? So this component V cos theta and B, there is no force. So this particle will continue to move as if there is no effect. Whatever is V cos theta, with the same velocity will continue to move forward because there is no force exerted on the particle because of this component. So your particle is exerted, it's moving like this, the magnetic field is in this direction. This particle does not experience any force because of this component, because this component and B are parallel to each other. So your particle will continue to move in the same direction without any deflection, but with this component of velocity V cos theta. But here V sin theta is perpendicular to B, which is the case that we just discussed. There also maximum force is acting on it, no work done, but it will put the particle into circular motion. So this component pushes the particle forward with V cos theta. This component puts it into circular motion. So if you combine the two, you have your particle moving forward, but it is also executing circular motion. So that is what you call as the helical motion. In the second case, when theta is 90, it is simply executing circular motion, staying there. But here it is executing circular motion and moving forward, and that is what you call as helical motion. So if you were to represent that motion, we have the helical motion like this, and this distance between this is what you call as pitch. So pitch is the distance covered by the particle when it moves, when it completes one complete circular motion. The distance travelled forward by the particle is what you call as pitch. Pitch is distance is velocity into time. The velocity with which it moves forward is V cos theta. So this will be V cos theta into the time period, because it takes one time period. The time taken for it to complete one circular motion is what you call as time period. So pitch, that is the distance travelled forward by the particle when it completes one circular motion, called pitch, is V cos theta into t. So we discussed the three cases when a charged particle enters a magnetic field. If the particle is at rest, then of course no force is acting on it, because Lorentz force is F equal to QVB sin theta. If V is 0, no force is acting on it. It will behave as if there is no magnetic field. Second case, we took theta 0 or 180. The V is parallel to B or V is anti-parallel to B. Both cases, no force acts on the particle, no work done, so no change in its velocity. Particle will continue to move undeflected as if the magnetic field doesn't exist at all. In the second case, we saw that V perpendicular to B would mean maximum force acts on the particle. So a particle will, instead of continuing in its initial direction of motion, will now change its path. It will change into a circular path, the plane of the circle being perpendicular to the magnetic field. There also no work is done, so there is no change in the magnitude of the kinetic energy or magnitude of velocity, but continuously changing direction, so it is accelerated motion. And the third case is what we discussed here, helical motion. Okay, thank you. So that's the end of the second session, and then we'll go on to the third section later. Bye.